Okay, guys. So I just pulled this PowerPoint from the textbook web page, and I tried to cut out all the fluff. So the first 21 slides is what I covered yesterday when I was at work. All the simple gas laws, the combined gas law, and the ideal gas law. So slide 22 talks again about the ideal gas law. It shows you the relationship that we learned with our simple gas laws. There they are, and how that led to this equation. Okay, and then again, here's a reminder of what all of these terms mean and your constant. So let's keep going. This is just another way you could look at it in terms of your three simple gas laws, but you can look through that yourself. I'm not going to spend much time on that. Let's look at standard conditions. All right, so the volume of a gas is going to vary with pressure and temperature. So chemists agreed on a set of standard conditions to make comparisons easier. It's kind of like the standard states and the standard enthalpy of formation. So we set all these standards so that when we take a measurement, someone maybe in China who's doing similar research can refer back to our research and say, hey, okay, they did this under standard conditions and got these results, etc. So if you ever see in a problem the abbreviation STP, that just means standard temperature and pressure. Because again, your volume of gas depends on that temperature and pressure. So you need to remember these four standards. Standard pressure is 1 atmosphere. Standard temperature is 273 Kelvin or 0 degrees Celsius. People, myself included, confuse this a lot because in the last chapter, when we were talking about standard states, we wanted everything in 25 degrees Celsius. So I'll see that mistake a lot, and I make that mistake a lot. So just remember 273 K and 0 degrees Celsius. Okay? Then the standard amount is 1 mole. If we plugged the first three standards into our ideal gas law and we solved for volume, we would find that the standard volume of a gas at these conditions would be 22.4 liters. Okay. So we call this standard molar volume or simply standard volume. So we're gonna work problems with these standard conditions just as soon as I get through going over all of your formulas. All right, here is another note about the standard molar volume. So because it's for 1 mole, that means it's 6.022 times 10 to the 23rd gas molecules. That's just Avogadro's number. Y'all know that. sorry, my husband is, I sent him to pick up groceries. And we've never done the delivery, so I had to tell them that he was on his way. Okay. So just like for elements and molecules, 1 mole of something has Avogadro's number of pieces, but that never means that it weighs the same. Okay, and that's what this second bullet point is telling you here. In a gas, they will have the same volume because it's the standard molar volume, but it won't be the same mass. Okay, but I think we know that. Okay, next equation is the density of a gas. So if I want to know the density of a gas, I'm going to use its pressure, P, times this funky M is its molar mass. Oh, sorry. Molar mass. We're going to divide that by R, which is our gas constant, and our temperature in Kelvin. Okay. Another way to write this is to solve for the molar mass given its density. We would just rearrange this equation. So I'd multiply both sides by RT and divide both sides by P. And I would get that I could find the molar mass with density times R times the temperature divided by pressure. Okay, so we'll use that equation to find the density of a gas or the molar mass of a gas. This is a lot of equations, so if you haven't already started a formula sheet for exam 1, I don't know what you're waiting on. I will not give you these formulas. You have to remember the formulas and know how to use them. So I'd go ahead and start adding all of my gas formulas to my formula sheet. All right. Mixture of gases. So a lot of times we're dealing with a mixture of gases. When we breathe in atmospheric air, it's a mixture of gases. So how does that mixture of gases affect our calculations? Well, let's see. All right, so dry air is mainly nitrogen, a little bit of oxygen, very small amount of argon, and then an even smaller amount of carbon dioxide. Okay, so that is what dry air is, and you'll see here in this table 10.2 the percent by volume of each of those components. So 78% of dry air is nitrogen, 21% is oxygen, etc. So how do we handle a mixture of gases? Well, for our sake, the mixture can be thought as just one gas. So even though air is a mixture, its pressure, volume, and temperature can be treated as being one because those 3 variables are the same for every component of my gas, okay? I'm not in a room where I'm treating the nitrogen with one pressure, the oxygen with another pressure. It don't work like that, okay? They're all under the same pressure, same temperature, same volume. So if we know the pressure, volume, and temperature, the total molecules in the air sample can be determined, even though they are different compounds. So it's not very hard to deal with a mixture of gases. It's just a little extra work. So let's see. So we have Dalton's law of partial pressure. Dalton's law states that the total pressure of a gas mixture is simply the sum of the partial pressures. Okay, so the partial pressure is the pressure of each individual gas component. Okay, so let me back up. I said I can't have the pressure, I can't have one gas under a certain pressure and the other gas under a different pressure. That I meant external pressure. But each individual component has its own pressure associated with it, because remember, pressure is the force it exerts when it collides with the wall of its container or other gas particles. So each individual component of your mixture has its own specific pressure. I probably really just messed y'all up there. All right, so according to kinetic molecular theory, that's just a theory that we use to describe gases. The particles, the gas particles, have I'm really bad at pronouncing this word. Negligible size, and they don't interact. So here we're saying that particles of different masses have the same average kinetic energy at a given temperature. Because the average kinetic energy is the same, the total pressure of the collisions is the same. Again, I feel like I'm just confusing you. Basically, each gas has its own partial pressure. Okay, so if I have a mixture of gases and I want to know the total pressure, all I do is I add up the sum of the partial pressures of each component. Okay, so the partial pressure can be calculated in a few ways. I'm here on bullet 2. Sorry. We can calculate it if we know the fraction of that component in the mixture and we know the total pressure. Okay. Or we can use the number of moles of gas in the container of a given volume, and the temperature is known. Okay. So again, once we find the partial pressure of each individual gas component, to find the total pressure, we simply add those together, and that is known as Dalton's law of partial pressure, and that's right here. Okay, last bullet that's in bold. Gases behave independently, so they don't affect one another. Okay, so we try to like focus in on one gas component at a time and treat it as if it's the only gas there to make our lives easier. Okay, so to find the partial pressure of the individual components in a gas mixture, we're simply going to use the ideal gas law that has been rearranged. So the ideal gas law, PV equals nRT. If I only want to know, if I only want to know. If I know everything and I want to know the pressure, or I'm solving for pressure, I'm going to divide both sides by V. V cancels, P equals nRT divided by V. Okay, you'll notice that they pulled the N out here. That's because if I was looking for, let me see if it's on the next slide. Yes. Flip over to the next slide. If I am looking for, say the total pressure, each individual component's temperature and volume have to be the same. The R also has to be the same because it's a gas constant. So the only thing that will be different in each calculation is your number of moles of that component of your gas. Okay, so basically, if I wanted to write, I wanted to calculate my pressure, my total pressure, you'll notice down here that you just add up your partial pressures. But what if I don't know them and I would have to calculate them? Well, one way to save time would be to pull out the moles of each component, add them together, then multiply that mole number by R times T and divide by V, because the RT over V is the same for every one of these. Okay, so that's one way you could find your total pressure if you weren't given your partial pressures and you had to do this. Okay. This slide says exactly what I just said. Okay, so they pulled out the number of moles. Again, this is the same for every component. So I could just add all my moles together, multiply the total number of moles times R times T divided by V. I would get the total pressure of my mixture of gases. All right. Well, sometimes you have your total pressure and you want to find your partial pressure of each component. Well, if I wanted to relate a component's pressure, one partial pressure, to the total partial pressure, this is what it would look like here. But I could substitute in for the fact that the only difference in these, my PA and my P total, is the number of moles. Because again, R times T over V is the same for the whole mixture. So then it would just be what is called a mole fraction. It's your number of moles, the A part over the total part in a fraction, so it's a mole fraction. So we actually have an abbreviation for that. It's this funky looking Greek symbol. And it is simply that. It is part over whole. That's what a fraction is. Okay. The part I'm interested in over the whole thing. So if I want the mole fraction of, say, substance A, it's the part A's mole divided by total mole. This is known as the mole fraction. Okay, so how would I use that in a problem? I hope it's on the next slide. It is. All right, so again, if I know my total pressure and I want to find my partial pressure, I can do that as long as I can get a mole fraction. So I would have to know the number of moles of the component I'm interested in and my total number of moles. I would calculate my mole fraction. I would multiply that by the total pressure. I would get my partial pressure for substance A. Okay, so here's an example. For gases, the mole fraction of a component is equivalent to its percentage by volume divided by 100%. In other words, it's a mole fraction should always add up to be 1. Okay. So we learned, or I told you in a previous slide, that dry air was 78% nitrogen. In other words, its mole fraction is 0.78. If the total pressure of dry air is 1 atmosphere, what is my partial pressure? Well, I would simply take the mole fraction of nitrogen times the total pressure. I would get, the partial pressure of nitrogen. Okay, so I could solve another way they showed down here is you went through and solved all the partial pressures and you add them together. They should equal your total pressure. It's one way to check, make sure you've done everything correctly. Okay, let's see what's next. This is just showing you the difference in total pressure at the surface of water and then 30 meters below sea level, and the difference in nitrogen and oxygen's pressure. So you'll notice that 30 meters below below sea level, your pressure is extremely high. Your nitrogen pressure is much higher than normal, as is your oxygen. So this can be very dangerous. So when you breathe in compressed air like that abnormally high partial pressure of oxygen leads to an elevated concentration of oxygen in your body tissues, which can lead to oxygen toxicity. Okay, so it's one reason I don't go deep sea diving or anything. Just kidding, I wouldn't anyway. All right, the last thing we will use in this chapter, give me just a second. All right, so the last thing we're going to do in this chapter is stoichiometry with our gas laws, or mainly with our ideal gas law. So we can apply what we've learned in this chapter and what we learned in Chem 1 to gaseous reactions. And we can figure out how much, if we react to gases, how much of another gas it will produce, and vice versa. A lot of times you might be asked to find the moles. Other times you might be asked to find volume. Either case, you simply are going to rearrange your ideal gas law in some way so that you can figure out what you need to know to go any further, okay? So if we have to figure out moles of a reactant, that might not be the final step. We might have to use that mole of reactant to go to moles of a product, or maybe even grams of a product, okay? So it's not difficult. It's just applying two things together, okay? Not bad at all. Here is a conceptual plan if you like those. If you know me, you know I prefer to watch my units cancel. When I do that, I can almost work any problem without having any sort of plan, okay? But if you like to plan, then maybe this is for you, okay? All right, so just to summarize gases and their basic properties, before we dive into the math, here's a summary. Remember, gases expand to fill their container. They use up all the space they can. They take the shape of their container. They have low density. They're much less dense than both solids and liquids. They're compressible, so you can compress them if you have like a piston. And that goes back to PV work that we talked about in chapter 9. And then mixtures of gases are always homogeneous, meaning they mix and they look the same throughout. Okay. All right, so now we are ready to work some problems. So I before I knew that I'd have to quarantine yet again, I went ahead and printed out a PowerPoint with all the examples that I'm going to work. Well, I can't find an electronic copy of that PowerPoint, so I had to throw one together real quick. I hope it works. I mean, it will work for the sake of what we're doing. But if I were you, I'd go pick up a hard copy outside of my office. They're in the clear bin. I printed enough for everyone to have one copy only. If you can't get by there, I will, of course, post an electronic copy on Moodle so that you can follow along with me. So that will be part 3 of chapter 10. Be back soon.